Hello, so today with this video we're going to start hopefully a long series of videos about analog sound synthesis. So most of the material from those videos is going to be taken from the excellent book Make Analog Synthesizers by Ray Wilson, and Ray Wilson is the person behind the Music from Outer Space website. And we're going to focus on what is called the Noise Toaster, a pretty neat analog old school synthesizer. And the first thing we're going to look at is what is called the attack release envelope generator, aka AREG. The synthesizer is controlled by a keyboard controller. I mean, not always, because some people they prefer to just play with the buttons to get all the notes. But I mean, in the real world, and to be practical, it's much easier to have a keyboard to control the frequencies of the sounds you want to generate. So this attack release envelope generator is basically controlled by what is called a gate voltage. So for example, when you press a key on the keyboard, and I'm showing this in black here, this is the voltage and this is time. So when no keys are pressed, you get 0 here, so no voltage. And when you press a key, the gate voltage goes to its high position. So let's say if this is 0, it goes to, let's say, 1 volt, or it could be 5 volt, whatever. And as long as the key is pressed, the gate stays at this level, and then when the key is let go, the gate voltage goes back to 0, or it could go back to -1. I mean, whatever, it goes back to its low voltage basically. So at the same time, what happened in that attack release envelope generator, AREG, is that, and this is the V out of that thing, this is V out, in what's in red is the output of this AREG. So when the gate is at its low, the V out is 0. When a key is pressed, so the gate goes to its high state, and this starts what is called the attack. So the voltage is going to ramp up. The voltage is ramping up to this level. How long this takes, this attack phase, it's going to depend on the potentiometer, a pot on your synthesizer. So now you are done with the attack, and now you are beginning what is called a sustain phase. And here the voltage is constant, it doesn't change. And then when the key is let go, the array goes into its release phase, and basically the voltage goes back down to 0. And again, the time it takes to release is going to depend on a pot on your synthesizer. So this is basically a simplified version of the ADSR envelope generator. So what's missing here is the decay. I mean, if you had a fully-fledged ADSR envelope generator, you would have like a decay here. So you would have a decay here and then the sustain. So here it's a little bit simplified in a sense because you don't have to deal with the decay. So you have an attack, sustain, release. Very simple. Okay, so this is the LTspice simulation of the attack release envelope generator. And here, when compared to what's in the book, I simplified it a little bit because in the book he has a switch that enables you to do a repeat, and I don't think it's that interesting to do repeat. So I'm just assume that S switch number 8 is always on manual. So meaning that the gate has to be applied manually. So if you look at the schematics on the book, he has like a switch number 10, which is the manual gate. And this is what I have here. The S1 is that switch. But of course, I don't control it manually. I control it with a pulse. Okay, so it's the equivalent of applying a gate. It's the same thing. So when the switch is off, it's at this voltage here, because this is B positive, which is I think 9 volt. So when the switch is on, you get 9 volt here, otherwise you get 0. Actually, this circuit is very simple in the way it works. There's a transistor here, Q10, that's a PNP transistor, and its only purpose is to discharge this guy, capacitor C1. That's the only purpose of this transistor. And why it put a PNP there instead of NPN, I'm not sure, but it doesn't really matter. So you have the PNP. And remember, the PNP, how it works is that you have to put the emitter on the positive side of the battery. So here, let's say you have 9 volt. Let's say you have 9 volt here. So this is the emitter, this is the base, this is the collector. So if you have 9 volt here, in order for the transistor to turn on, this base voltage has to be lower than BP minus 0.7. So if BP is 9 volt, for the transistor to turn on, this base voltage has to be lower than 8.3 volts. If the base voltage is equal to BP, then the transistor is off, and the capacitor here cannot discharge. You can see the path from the capacitor through R50 through the release time potentiometer, the diode, and then it goes to the emitter. Okay, so the path going from here up has to go through here because of the diode. Okay, that's pretty cool. So you have a diode that goes this way and the diode that goes that way. So that's the purpose of the transistor. It's only to discharge. Its only purpose is to discharge this guy. Okay, what's the purpose of this guy here? This is a JFET. I think you could have used a MOSFET here, but he's using a JFET, fine. And it's, okay, so the JFET, so this is the gate here. This is the gate, this is the drain, and this is the source. And in this configuration, it's a common drain amplifier, aka a source follower. So its only purpose is to buffer here. Basically, it's to prevent C1 from discharging here. Because let's say that there was no JFET here, and the Vout was here. If the Vout is here and you connect something else like your voltage control amplifier, then the C1 is probably going to be able to discharge through that next module. That's why you have something with a very high input impedance here to prevent that from happening. And on top of that, it's a unity amplifier. So the Vout you would get if there was no load is the same as the Vout here that you can get if you put something after that. So again, this is a common drain JFET amplifier. It's very similar to the common collector BJT amplifier, aka emitter follower. Okay, so let's go into it. So what happens? Let's see what happens when the switch is on. So switch is on. What happens? That you connect BP here. So now this is BP at this point. BP. So here you have BP, here you have BP, and here you have the basically 9 volt across that R61. So where does the current go? The current is going to go this way through that R57. Okay, here it cannot go here because here you have, okay, so you have BP. So BP is the battery positive, aka 9 volt or 12 volt. I think I use 9 volts here. Yeah, I use 9 volt. So, okay, 9 volt. You have 9 volt. Here, there's no current. Here, there's no current. Okay, there's no current. So here you have 9 volt. Here you have 9 volt. So you have 9 volt here, 9 volt there. Transistor is off. So the current has to go, it cannot go this way. It has to go around it. So it's going this way, that way. Then it's going through this diode. And then it's going to go through the attack time pot on your synthesizer. And then it's going to go through R50. And it's going to charge. It cannot go in there because the current cannot go inside the JFET because it has very high impedance. So it's basically charging C1 a little bit of time. Then you're probably going to have 9 volt or close to it at the gate. And again, because this is a unity, I mean less than unity amplifier, you end up with the output right there. So again, this is a common drain. So you have no resistor on the positive side, and the output is right here. So this is basically the attack phase. And if, as long as you keep that switch closed, that voltage is going to stay at that level. And this is basically the sustain. And now if S1 is open, you're going to start the release phase. So what happens in that case? So when you open the switch, the gate is going to be at ground level, and this guy here is not at BP at the BP level. It's going to be at the level of the whatever is on this side of the capacitor. So let's say it's going to be 9 volt. So that's going to turn the PNP transistor up there on. So now you have a path from here to ground. So what's going to happen is that the C1, it cannot go here, but it certainly can go there now. It's going to go this way through R50. Then it's going to go through this one, this pot, the release time pot, this way, through the diode, through here, through the emitter, and then right through the ground. So it's going to discharge. Okay, so that's the idea. And then you can repeat that. You can press again, and you get the same thing over again. So this pot controls the attack time, and this pot controls the release time. So let's run this thing. I think for this first run, I set the pot at 200K and the other pot also at 200K. And then we're gonna step over different values. So let's run this thing. So let's look at the output. Okay, and you can see that here you have the so basically this is the attack around here up to here, sustain, and this is the release. Okay, so now if I go back to that thing, and then I'm gonna step over different values. So you can step over different values for the attack time and for the release time. I'm gonna do the, let's say I'm gonna do the attack time. So I need to change this one to a comment. I'm gonna comment out this one, and I'm gonna turn on that one. So this is gonna play with the attack time. So let's run it. V out. Okay, so this is the fastest attack time. Then it gets slower and slower to a point where you don't even reach the sustain, but you get the idea. And then you can do the same thing on the release. So I'm just gonna comment this one. I'm gonna put this one back on, comment this one, and turn this one on. Okay, so now I'm going to see the effect of changing the pot for the release time. Okay, V out. Okay, so here you have this is the release. So here you have the quick release, and then you get slower and slower releases. So that's the idea. Yeah, so this is a pretty cool circuit. Very easy to understand, I think. Yeah, so I went back to fixed values for both pots. So anyway, what do you do with this thing? Well, you can feed that control voltage, which is basically a voltage envelope, to the voltage control amplifier, so that when you press the key on the keyboard, the level of sound doesn't reach the full intensity right away. It goes through that attack, and when you remove when you let go of the key, the sound level doesn't go from full on to full off. It goes through that release time. So it's just a nice, it's like a piano. So you have attack, sustain, release. So you would feed that control voltage to the next module, like the voltage control amplifier, but you can feed it to other stuff like the voltage control filter, whatever is voltage control, whatever you can find that can be controlled by voltage, you can feed that thing to it. So I'm going to stop here, and of course I'm going to include the simulation file in the description.